Welcome to the presentation for our ICTIR paper, Taking the Counterfactual Online, Efficient and Unbiased Online Evaluation for Ranking. My name is Harrie Oosterhuis. I'm a PhD student at the University of Amsterdam, and this is joint work together with Professor Maarten Rijke. I'll jump in straight into the main contributions. In this paper, we introduce a novel algorithm called the Logging Policy Optimization algorithm, which takes counterfactual evaluation for ranking and turns it into an online evaluation method. We also provide proof that existing interleaving methods are biased with respect to rank-based position bias. All right, so let's get started. The main task that we address in this paper is given two rankers, or you might say ranking systems or ranking policies, which of the two results in the highest click-through rate. So which one gives you the highest click-through rate? Online evaluation methods are methods that show rankings to users, observe their clicks on these rankings, and based on these clicks, they estimate the absolute ICTIR click-through rate difference, so how big is the difference in click-through rate between two systems, or the binary click-through rate difference, meaning which one gets the highest click-through rate of the two. And what we do here is we'll focus on three properties that these estimators or online methods can have. The first one is consistency, which means does the estimation of the method converge as more data is gathered? So if we get more and more data, does the estimation converge on some value? Unbiasedness, which means that the expected estimate is equal to the true click-through rate difference. This just means that it's going to, expectation be correct, like it's going to match the true click-through rate difference. And lastly, we have variance. This is the expected difference between a single individual estimate and the mean estimate. So all of these methods will have many individual estimates and they'll average over it. And the variance looks at the difference between these individual estimates and the result of averaging. The perfect valuation method, the goal that we wish to have, is an estimator that's consistent and unbiased. So it's going to converge on the true click-through rate difference, but also we want it to have minimal amount of variance, the least amount of possible variance. That means it's going to converge as quickly as is possible. All right. Before we dive into the methods, we have some preliminaries. We make one assumption in this paper on which we base the theory. That's rank-based position biased click behavior. That means that we assume there is position bias in these clicks, but it's rank-based. To put that formally, here we have the click probability of a document D in a ranking R. So given that document D is displayed in ranking R, the probability of someone clicking on D is the probability of examination, which is conditioned on the rank of the document. Usually the higher the rank, so the closer it is to the top of the ranking, the more likely it is to be examined by the user, and the relevance, whether the user considers it relevant or not, which is conditioned on the document. So the assumption is basically that we assume a click means someone examined a document and thinks it's relevant, and whether someone examined it or not only depends on the rank at which you display a document. This is a very common assumption in counterfactual learning to rank and also in a lot of click model work. You can see it as the most basic form of position bias. Let's look at some existing methods. I'll start with A/B testing, very general method, very common, very straightforward. You divide your user base into two groups, expose each of them to a different system. You can observe the click-through rate in each of these groups, and that gives you an estimate of the click-through rates of both of these systems, so also the difference. It's consistent and biased. The variance depends on a lot of things, so we'll see more of that in the experiments. Then we have interleaving. Interleaving is specifically designed for this task of comparing ranking systems. They take the rankings of different systems and combine them in an interleaving way. They all do it quite differently, but you get a combined ranking which represents both of the ranking systems in some way. And when users click on documents in that combined ranking, we can interpret them as a preference signal between one of the two systems. So the methods that we combine here are team-driven interleaving, probabilistic interleaving, and optimized interleaving, which you could argue are the most prevalent interleaving methods. The properties are, all of these are consistent. They all converge on some value, but they are biased. We show this by a proof by example. So if you go to the archived version of this paper, you can see the paper in the appendix in one PDF, and you'll see in the appendix that we provide an example for each of these methods where the click-through rate of one system is higher than the other, but the interleaving method is going to converge on finding the other method preferable. So it's going to prefer the system with the lowest click-through rate. Thus, it's biased with respect to rank-based position bias. The last evaluation method I want to look at is counterfactual evaluation. Counterfactual evaluation is the basis for counterfactual learning to rank, which uses inverse propensity scoring estimators. What it does is it takes biased historical data, so clicks that were gathered in the past, and unbiases them by reweighting the clicks, or by weighting the clicks, I might just say. The intuition here is, if you remember, probability of a click was the probability of examination times probability of relevance. But that also means that the probability of relevance is the probability of a click divided by the probability of an examination. It turns out that getting the probability for a click is quite easy because you can observe clicks, so you can get a frequency estimate very easily. And there's methods to get the probability of examination as well. So once you have those two, you can unbiasedly estimate the probability of relevance with an IPS estimator. To unbiasedly, so the nice thing now is, if we can go a step further, we can unbiasedly estimate the click-through rate difference on a ranking, let's say R prime, from clicks on a different ranking, let's say R. We do that by the formula you see down here. So the probability of a click on R prime is the probability of a click on R divided by the examination probability on R times the examination probability on R prime. Now this is very useful because it means that you can observe clicks on a different ranking and estimate unbiasedly the click-through rate on the ranking that you're interested in. We use the policy-aware estimator. This is from recent work that we did for ICTIR, so it's extremely recent. Here we use a conditional examination probability that's conditioned on the ranking policy instead of the ranking. So we now have the probability of examination under the policy instead of the individual ranking. And this is based on expectation. So we just sum over all the rankings that this policy might show, and then we take the probability of the policy showing that ranking times the probability of examination in that ranking. So this tells us, if I use this ranking policy, how likely is a user going to examine this document? All right. Now, when we're comparing two ranking policies, we'll use an estimator that uses this function that I just put on screen for its individual estimates. I don't have time to go into the full details. Please read the paper if you're interested in that. But the idea here is that we're comparing the ranking policy pi1, or ranking policy 1, and ranking policy 2, or pi2. But the clicks have been logged on with the logging policy 0, or pi0. Now, a single unbiased estimate from a single query interaction. So somebody issued a query, we showed a ranking using the logging policy, and we observed clicks. And now we want to convert that into an estimate of the click-through rate difference between pi1 and pi2. Will look like this. We're going to sum over every clicked item. Again, this is on the ranking shown by the logging policy. And then we're going to, for the clicked items, we're going to take the difference in examination probability between policy pi1 and minus policy pi2. So how much more likely is this document to be examined under pi1 than under pi2, divided by the probability of examination under pi0. This is to remove the effect of the bias introduced by the logging policy. And I'm going to use the shorter notation lambda d and rho d, where lambda d is the difference in examination probability between pi1 and pi2, and ρd is the propensity. So in this case, the probability of examination under pi0. All right, so this gives us this unbiased estimate for a single issued query. Now, that was background so far. Let's see how we go to our novel algorithm. The main insight here was that this policy-aware counterfactual estimator is consistent and unbiased. It's going to converge on the true click-through rate difference, if we know these examination probabilities, of course. But assuming that we do, it's going to be consistent and unbiased. But the variance depends on three things: the rankers in the comparison, the click behavior of the user, including its position bias, and the logging policy that's used to gather these the clicks on which this estimate is based. And the key insight here is that we have control over that logging policy. We can't control the click behavior. The rankers in the comparison are given, so there's not much we can do about that. But the logging policy, we have control over if it's run online. If we're still collecting these clicks, if we're not working from historical clicks, we can choose what logging policy to use. The idea here is that we use an optimization algorithm that optimizes the logging policy so that it minimizes the variance of our estimate. And this practically turns counterfactual evaluation into online evaluation. Counterfactual evaluation is agnostic to how clicks were gathered. It has some requirements, of course, but mostly it's oblivious to what's going on there. Whereas with this algorithm, we have an algorithm that prescribes the logging policy that should be used. And this is characteristic of an online method that really interferes and intervenes with what rankings are shown. This is a simplified graphic of how we're going to apply this algorithm. We have the logging policy on the left. It's going to provide us clicks, which we use for an unbiased estimate. But we're also going to use those log clicks to estimate the variance of our unbiased estimate, and then perform variance minimization to get a better logging policy. And thus we've started a feedback loop where we gather more clicks, which allows us to better estimate what the best logging policy might be. And then we use that to update the logging policy to gather more clicks, and again to estimate the variance again, and we can do this repeatedly. That's the main idea behind this algorithm. I want to give you some intuition about the mathematics, even though I can't go into full detail because we don't have the time. But I wanted to take a look at together with you at the variance for this estimator. So we're going to look at the variance conditioned on a single query. If you have that, it's very easy to get the variance on the total query distribution. And we have to sum over every possible click pattern. Now with a click pattern, I mean a combination of clicked and non-clicked documents. So a subset of documents clicked and the rest isn't clicked. Any possible combination or any possible subset counts as a click pattern. Then we have the probability of the click pattern. This depends on the logging policy that's going to show rankings, but also on the click behavior of the user. That's how likely we are to see a certain click pattern. Then we have the error that click pattern of the estimate that click pattern leads to. So we have the true click-through rate difference and the estimate that we would get from observing these clicks. Now they're probably not equal. There's some error here, and that's going to lead to the variance. Right? So this is a very straightforward way of defining the variance. Sum over all possible click patterns, take the probability of that click pattern times the error that pattern would lead to. Now, if we take the gradient or the derivative, something interesting happens. We see there's two conflicting goals. So this is just a product rule, but it tells us that on the one hand, we want to minimize the frequency of high error click patterns. If a click pattern leads to a high error, we want to avoid that click pattern happening. So we want to avoid showing rankings that may result in that click pattern, right? So for instance, if we don't want a document to be clicked, we'll try to put that document in a place where it's less likely to be examined. However, the second part of the derivative is somewhat conflicting. It tells us to minimize the error of frequent click patterns. So it tells us to change the logging policy so that the propensity score is changed so that the error is reduced. So that means that if we're pushing away a document, making it less likely to be examined, propensity goes down, so the inverse propensity goes up, which could lead to a really high error. So on the one hand, you want to avoid showing a documents that lead to high error, but if you avoid showing it too much, that actually can lead to an even greater error when it's clicked. And that's where a balance comes in, which this gradient naturally resolves. So we use stochastic gradient descent to optimize the logging policy. There are two problems here. We need to know the relevances to also the examination probabilities to calculate this gradient, and they're unknown, but there are methods for estimating them. So we use expectation maximization. Estimating these values is good enough to update the logging policy, and still you can still get unbiased estimates. The other problem is that these derivatives are computationally infeasible. We have to sum over all possible click patterns, all possible rankings. That's not doable in any sort of normal amount of time, but you can approximate these gradients with Monte Carlo sampling very easily. Let's look at the experiments. We simulated 1,000 comparisons based on 2 commercial learn to rank data sets, where we simulate position biased clicks. So we generated 2,000 rankers. Each was trained on a random sample of 100 queries and 50% of the available features. So they all have different information during training, resulting in different ranking behavior. Here you see the distribution of click-through rate on these 2 data sets. It appears to follow a normal distribution. And we compared pairs of these, resulting in 1,000 comparisons. Quite a large, a really large number of comparisons. And I want to look at the absolute error with you. We also looked at the binary error in the paper, but the absolute error is easier to understand. So what you see here is, note the log scale on the absolute, on the y-axis showing the absolute error, and the x-axis showing the number of queries issued. This black line here is A/B testing. If we look on the left on Yahoo, we see it's the slowest of all these methods, but it's unbiased. It leads towards a 0 error, as you can clearly see. If you compare that to the yellow, the green, and the blue line, which are all interleaving methods, we see that they're initially have a much lower error, but they're clearly biased. They converge on an error of at 1% or so. And even when they have 1,000 times the number of the amount of data, 1,000 times number of queries, the error doesn't go down. So this clearly shows us they're biased. If we compare it to LogOpt, which is this red line where position bias is known, and the blue line where position bias is estimated, we see that it's faster than A/B testing, but unbiased, just as unbiased. What we've done here is we applied this algorithm every factor of 10. So at 100 queries, at 1,000 queries, 10,000 queries, etc. So you can see, for instance, a drop in the blue line at 1,000 iterations because it has a better estimate of position bias. So LogOpt seems to be, on the Yahoo dataset, more than twice as data efficient. It needs half the amount of data to get the same error. On MSLR, it's not as clear, but it's still comparable. So it's at least as efficient as A/B testing. And on the Yahoo dataset, it seems to be much more efficient. All right. We also looked at other logging policies. So we looked at a uniform logging policy, a logging policy where you show one system 50% of the time, the other one the other 50% of the time, A/B testing. And then Oracle, where we use the true relevances. And again, we see big differences. Again, this is a log scale, so small differences are actually quite large. Uniform logging policy is a terrible choice. A/B logging policy is a better choice, but LogOpt is near optimal. It appears that knowing the true relevances isn't that important when you're trying to find the best logging policy. All right, to conclude the talk, we've shown that by optimizing the logging policy while you're still gathering data, you can turn counterfactual evaluation into online evaluation. We introduced the logging policy algorithm that does just that, and our results show that it appears to be as efficient as online evaluation methods. We also proved that interleaving methods are biased with respect to rank-based position bias, at least, and we really think that further research should consider the impact this may have in practice. These are my references. Thank you very much for listening. And, bye.